Okay, thank you very much. So yeah, good afternoon. So thank you very much for giving me the opportunity to talk to you today about the work that we're doing in my group. This is going to be less about techniques and more about materials. So we work in sustainable materials for energy applications. So before I go into more details, I just wanted to introduce my research group. So my group started in 2016. So as the introduction say, I moved from UCL when I was a postdoc to start my independent career as an academic at Queen Mary University of London. So in 2016. So the group has slightly changed over the years. And now we are 6 PhD students and 1 postdoc. And we all do slightly different research, all related to energy storage and energy conversion, but all also with a focus on developing functional materials using sustainable resources. So that's a little bit what I'm going to talk about to you today. So a little bit on the motivation. Of course, everyone is aware of climate change, global warming, how the use of sustainable resources and renewable energies is key to help decarbonize our electricity. So this is the main motivation for us. And here we can see clear graphs showing the global temperature progression over the last almost over 2 centuries. So it's a reality, and we need to. It's not going away. So we really need to face it and do something about it. So now everything it's bad, and you know it says that obviously steps towards the right direction, but however they felt that these steps feel a little bit somewhat slow and perhaps also a bit late. But we can see in this graph there's been a massive increase over the last almost 20 years in increasing capacity, installed capacity for renewable energies. But we can also see that in the last few years, that increase has slowed down a little bit, and that has to do with actually the capacity that we have to store that electricity that we install it. So it doesn't matter that we have like over 100, maybe 70 gigawatts installed capacity if we can't really store it effectively. So that's the key part that we need to fix in order to be able to realize the use of renewable energies effectively. And so here we have another graph showing, in this case, is not installed capacity for renewable energies, but is the ongoing projects in developing capacity to store that energy. And you can see the number. It's much lower than that installed electricity. So it's like 3.69 gigawatts versus the 170. So and also we can see here the trend. So perhaps you cannot read it very well, but I'll read it for you. So the purple one is the thermal storage, which has increased over the last years quite significantly. The electromechanical, which is this green now, one's been quite the same over the last years. And then also it's started increasing quite a lot the electrochemical storage, so batteries. So this is very good. So this is where our motivation comes from. So energy is electrochemical storage, so batteries. So the first battery ever invented, is like this one that we can see here in these pictures. Things have changed a lot since 1800 with Volta developed these first batteries. So batteries in that time, they were primary. That means that once the reactants were used up, the battery were working more, so they are very short lifespan. So everything changed with the development of the lithium colloxide as a positive electrode for lithium-ion batteries by Vinov in the 80s. So this changed everything, because that meant that the batteries could be actually rechargeable, And that led to a complete revolution in the field of electronics, and now more recently also in electric vehicles. So all that, it's obviously a great development in our society, and it's changed a lot of things. So, but obviously there's a lot of there's some side effects to the development of these batteries, and obviously these batteries are rechargeable, but that doesn't mean that they last forever. They also have a lifespan, and now we need to think about what we do with them, because these batteries have more complex components. All the different metals of electrodes are quite challenging to separate and to recycle, to reuse them. So that's the next challenge that our society is facing, if you like. So we have to take this figure, for example, here. It shows how, you know, it's quite difficult to balance that performance versus sustainability, and you know, keeping a low cost as well. And this here, I think it's a representation of what we are now, which are like all our batteries are essentially based on lithium, commercial ones mostly. But then the idea is that in the next generation, we will move towards lithium-based chemistry, but that lithium would ideally be being sourced from used lithium-ion batteries, and then in the future, just try to perhaps move beyond lithium. So Lawrence was talking about, you know, sodium and calcium, you know, all the chemistries that are being researched at the moment, because of the several reasons, sustainability, but also lithium is sort of reaching its maximum potential. So I'm trying to look into different alternative chemistries that can lead to a more sustainable future, and also a lower cost and keeping the performance. So that's why all the research in that area it's now being really really developed. So as I said, I'm going to talk about materials and sustainable materials. So the idea or the situation, or the question we ask ourselves is, can we make sustainable materials, but that they're equally efficient materials? That will be, that's our aim. So I took this sentence like from Donald Sadoway from in a very inspiring talk where he talks about his development on molten salt batteries, which is quite good. And he said, if you want to do something that cheap, just make it out of dirt. So taking that sentence and statement, you know, we work in our group, we work with biomass dirt, so biomass waste. And when you have a look at the different molecules that contain the biomass contain, they're really, really complex and interesting. And you can see how potential, you know, by tuning them and treat them and do things with them, you can actually get quite interesting compounds that can lead to energy materials, believe it or not. So that's going to be the core of the talk a little bit. So obviously we have a biomass like that, but we need to be able to process it in a way that we can actually use it. So the process that we use in our group is called electrospinning, and I'm going to talk about lignin because it's where most of our efforts are focused at the moment. But we also working with other types of biomass like algae, and we also work with them. Sugarcane and another type of and shells, coconut shells as well, but I'm going to focus in this particular one for this talk. So electrospinning. So for those who are not familiar with the technique, the electrospinning is a technique that enables the formation of non-woven fibers by applying a high electric voltage charge between a needle from a syringe, which is metallic, the needle, and then a current collector that is also metallic to establish the high voltage between those points. And inside the syringe, what we're going to have is a solution, which is our precursor solution, will contain the main precursor of the fibers, the materials that we want to prepare, lignin in our case. Then you can add, if you want, some additional polymers. This is if a precursor that you're adding it can be like a ceramic one, so you might need a polymer to help form the fiber shape that can then be removed after thermal treatment anyway. And then you need a solvent to have your solution, and then you can add a lot of different components, like for example, if you want to tune the porosity, you can add surfactants as well, or you can add a post-treatment of KOH, and then you can add also nanoparticles of different electrocatalysts as well that will then embed in the fiber as you're spinning it. So that's a lot of options that this technique allows to. So, and that way we have prepared different. This is just an example of some of the fibers that we prepare in the group. So these ones are tantalum nitride. So as I say, it's a ceramic. Not all of them has to be carbon based or polymer based. So so it was actually tantalum oxide that then was nitride under ammonia. Gas, then here we have some nitrogen doped carbon fibers with some iron tyrosine on the surface, which is like an oxygen reaction catalyst. And then here we have as well these fibers that have like carbon, but then all these flakes are manganese oxide, and this one finds applications in supercapacitors. So as you can see, completely different textures and compositions that we can achieve with this technique. But as I mentioned, we are particularly interested in developing materials using lignin. Lignin is, as you can see here, is a very complex molecule that also it changes depending on what the source of a lignin is, so depending on what tree or where you're getting from. We have a collaborator, an industry in Sweden. They do paper, so it's a paper industry. So lignin is a waste for them. After all the fractioning and after all the processing to obtain the cellulose for them, they end up with this powder that you see here, which is the lignin. So that's what we get, what they send us. And what we do with that is put it in the syringe, and then with this NaH solvent and another copolymer, although now we have developed a method where we don't even need to add any copolymer, just with lignin, we're able to form the fibers. We obtain something like this. So I don't know, I think it says there it's like 30 centimeters or so long, but which is quite good for the sort of experiments that we want to do. But that's that as prepare. Then we need to have stabilization treatment at 300 degrees C, and then a thermal treatment at 900 degrees that makes those aspon fibers become a highly porous conducting electrode that is also freestanding. And also this is going to be a very good advantage of these materials. The fact that we can actually do self-supporting electrodes means that we don't need to be putting an ink and spraying it onto a membrane or spraying into a current collector. We can just use that and assemble it and in our device, which is quite handy. You know, it saves a few steps along the way. So that's also very good. So these fibers are fairly elastic, but then again, this can be tuned depending on what sort of what amount of polymers you put and what sort of polymer you put. And then the surface of these lignin fibers are repopulated with a lot of functional groups, mostly oxygen, which is going to be beneficial for, particularly for one of the applications I'm going to show later, which is redox flow batteries. And then they're easily highly porous. And then again, this can also be tuned depending on the amount of polymer and the different modifications that you do to the fibers. So that's sort of like the characteristics and features of the fibers that we can produce. And this figure I also wanted to just highlight that along with the advantage that comes from using a more sustainable material versus a petrol-derived one, which is like this polyacrylonitrile polymers. It's not only that they're more sustainable, but you end up with materials, because they're completely different, you end up with more disordered crystallites that lead to a different type of porosity, a little bit chaotic, and I guess that is also a little bit of a downside. It's usually makes materials very difficult to characterize when it comes to biomass derived materials, and also, as I was mentioning earlier, sometimes they're difficult to reproduce if the source is not exactly the same one. So that has to be taken into account when you're working with these materials. But at the end of the day, it's a balance between these characterizations and reproducibility, and the fact that we're using sustainable resources. So yeah, and in this figure, what I wanted to show you is that recently acquired this sort of medium to large size scale electrospinner. So this is a little bit different to the one that has been explaining before. So we have the other one for sort of a small scale testing of different conditions, and then this one actually doesn't have a syringe. But you put a solution here, and then this is stationary wire electrode, and then what you do is move the solution up and down, and then the fibers deposit on that substrate that you have there, and then what you do is just peel it off, essentially. And in 40 minutes, we can get up to 35 centimeters area, which is really good, and then we could play with the thickness as well, and with different aspects. So this is going to be the next step once we have our materials. So the idea is that we can make this biomass lignin-derived fibers electrodes competitive with the current commercial materials that are used for the different applications. So here also I just wanted to show the electrospinning. It's a very flexible, tunable technique, and because of that, it's and how versatile it is for the application in different energy devices, because most of them are quite flat. And then because we're producing flat mats, this is very good. So they're applying redox flow batteries, metal air batteries, capacitors, and fuel cells. Yeah. So now I'm just going to highlight two main applications of these fibers. Some of the material that I'm going to present is still ongoing research. So some of the results haven't been yet fully understand, but I just want to share with you what we can do with these fibers. So the first application I wanted to mention is some redox flow batteries. I don't know if you're familiar with the flow batteries, but essentially they are stationary energy storage devices that can be seen as something between a hybrid between a fuel cell and a battery. In that fuel cell, in that you actually flowing in and out your electrolyte. So here we have the pump, so in the positive side and in the negative side. And what we're doing is storing chemical energy that comes from the redox reactions of active species ions that we have in the catalyte and in the anolyte. So the most popular redox flow battery is it's called all vanadium redox flow battery. And what it has is it's got vanadium species in the positive and negative side. And the positive we have 4 and 5, and in the negative 2 and 3. So when you're charging, the vanadium 3 reduces to vanadium 2 and produce 1 electron, whereas in the other side, the 5, the 4 oxidizes to 5 with that electron. So, and then in the discharge process, the opposite happens. So that's what's the redox flow battery mechanism or working principle. So what we have here is the stack. So we'll have 2 electrodes. Those are carbon, usually carbon felts, and that's separated by a NiFe protoconducting membrane because protons are involved in these reactions. So and that's the core of the battery. One thing that is worth mentioning about these devices is that they have a unique feature that no other devices have, and is the possibility that that the capacity and the power are separated. So because the active species are actually containing tanks that are outside of the cell, that means that the capacity of the battery is going to be given by the size of the tanks and also by the concentration of redox active species in your electrolytes. So that's why a lot of work is going into trying to develop species that you can really have a high concentration of them in the electrolyte without depositing. And then the power of your battery is going to be given by the stack size, so by the number of cells that you have put together, or by the size of your electrodes. So and this is unique, and this also make them especially suitable for stationary purposes. So that's quite important. So without getting more detail into this, just the main thing that I wanted to say is that so the electrodes that I use are carbon electrodes, and then the active species come to the electrode to do the reaction and transfer the electrons that will go to the other side. So currently those electrodes are based in PAN, so petrol-derived carbons. The carbon felts are quite thick, and they're not really optimized for flow battery applications. And contribute massively to the losses and efficiency of these systems. So what we have done is, Maria mostly have done, is to develop our lignin biomass-derived carbon electrospun fibers to replace the carbon felts. So as you can see, we can produce smaller diameter fibers. We can produce higher surface area mats. With much more active sites that essentially are going to enable more electrolyte and active species to be in contact as they flow with the electrolyte, with the electrode and more active sites essentially. So we've done some research on this, and here I'm going to show you some of the results. So here we can see this is the lignin fibers compared to the commercial ones. This is the same scale bar, and you can see how much bigger the fibers, commercial fibers are. They also have this thing here that end up being some carbon additive to increase the electronic conductivity of the fibers. One thing that we were really pleased with was, this is XPS, is that our fibers, so the red is the biomass ones, had much higher number of mounted on the surface of oxygen functional groups, and this is going to be quite important for the for the flow batteries, actually, because the vanadium seems to attach to the oxygen functionalities of the surface to do the electron transfer and to do the reaction. So this is going to be quite key. So we're really pleased with that. And here we have some also X-ray tomography to actually see even in more detail what the difference are with the commercial and the lignin fibers. These key balls that you can see here, the artifacts from the electrospinning. So it needs to be sometimes when you electrospin fibers that you get these formations, but then that can be sort of optimized to try to reduce that amount. So yeah, and then when we tried the full cell testing, actually we could see that our fibers were much better performing than the commercial ones. So we're really happy with that. Obviously, we then need to still work in the stability, and that's ongoing research, but still really promising, because we haven't really optimized anything, just produce them without tweaking much on the actual electrospinning processing. So that was really good. And then we also did some tests trying to understand the role of the oxygen functionalities. So here, this is all our fibers, right? But we sort of tune the amount of oxygen groups that we had. And then, so these have like low amount, high amount, and this is higher, even higher. So we can see the current density is higher when we have higher number of oxygen groups, and also that the potential shifts to slightly lower values. So, and this is, as I was mentioning here, as you can see, you have different in the example we is showing the OH. It can happen with other functional oxygen functional groups, and even others as well, as I will show in a second. And then you can see how the vanadium species will attach to the oxygen and will interact interact with it to conduct the reaction of oxidation or reduction. So the presence of these functional groups at the surface is really key in trying to increase the performance and electron transfer of the vanadium species. So we also wanted to have a look at the effect of all the as functional groups at the surface. So it's been already reported that by using phosphate functional groups at the surface of carbon felts, actually that leads to a performance enhancement of the performance. As you can see here in this diagram, it seems like because you have like free oxygens available to react with the vanadium, that is going to sort of like multiply, if you like, the amount of sites that the vanadium has to react compared to just one OH. So this seems to be true for a more flat and less amount of flat electrode with less amount of functional oxygen functional groups to start with. But what happens with a surface like ours, when we actually have a lot of different, geometries with less flat structures, and which already is really highly functionalized. So, so in our case, surprisingly, we found that we have a negative effect by the addition of a phosphate, which I think was quite interesting, because it says that something different happens when you already have like your surface really functionalized. So here what I'm showing is an XPS of the phosphorus line, where we can see this is the pristine commercial electrode, and this is the electrode with some phosphorus top. The amount that we could introduce was really low compared to the amount that we could introduce in the case of our biomass fibers. And then it has to do with the fact that we actually substituting some of the oxygen functionalities by the phosphate, and the oxygen ones were already low to start with in the case of the commercial fibers. But anyway, Here what we see is like a CV taking a free electrochemical cell. As I said, like the effect on the commercial one, it's positive, although quite low, probably because of a low doping. Whereas in our case, so this one is the pristine. It performs much better than the lighter one, which is the phosphorus dop. So as I said, it seems like in our case, because we already have quite an active surface, the addition of a phosphate, which is quite a big group compared to just the oxygen, might actually block access to other groups that are already there. So that's our thinking. And then also when we test, because these were like using in a half cell sort of test, when we take it to a full cell, as we can see here, we also observe the same trends. So the addition of phosphate doesn't seem to be positive for the vanadium transfer. So that was really interesting, and I think now what we are trying to do at this stage, as I say, that's some results, but then some still open questions. What we're trying to do now is doing some in situ, some operando or test on using the quartz microbalance with some electrochemistry as well, in a collaboration with a group in Paris. So that's the next step, and also welcome to do some other suggestions to try to understand this. So we're now also trying to develop some testing with doping with nitrogen as well, and with sulfur. And see how the system behaves, and also versus other different redox active species rather than just vanadium. So yeah, very interesting, and a lot of work to do in the field. Okay, so the next part, the last part of applications of the fibers I wanted to talk to you about is the one that has to do with the oxygen electrocatalysis, which is also something that is related to batteries, right? So metal air batteries are an alternative to lithium ion that has been developed, in the last few years, and it doesn't matter whether they are aqueous metal batteries or non-aqueous metal batteries. So this is like a zinc example, and this is a lithium oxygen one. Both of them have an air cathode that is going to work by using oxygen reduction and oxygen evolution reactions. So these reactions are very important. They're also quite important in fuel cells, the oxygen reduction and oxygen evolution in water electrolyzers. So it's not surprisingly, but these reactions are really, really challenging. They have really high activation energies, and they're not easy to happen. So for them to happen, we need, not surprisingly, the use of really good catalysts that are going to be robust and stable under the harsh environment that all these devices work under. So here we have volcano plots for the oxygen reduction metal catalyst and the metal oxides in the case of the oxygen evolution, and we can see the best around platinum, palladium. Iridium is not that good. Iridium is better for oxygen evolution, but so you can see again, these are not very sustainable materials, and they're really scarce and are really difficult to get, really. So the idea is that can we try to develop alternative materials to this that are going to still perform at acceptable levels. So that's our premise, our goal. So so I have Lynn, PhD student group that is working on this type of materials. So nickel iron layer double hydroxide that are supported on carbon fibers, and these carbon fibers are also lignin derived. So So this layered double hydroxides are present a hexagonal phase. I don't know if you've seen these sort of materials before, but so they have like different octahedrods. Some of them have a cation on the 3+ oxidation state, and some 2+. And then they have these layers where they have they can have like water molecules. They can also have other anions depending on synthesis. They can be carbonate mostly, and then. What happens sometimes is that some of the nickel it's 2+, and then the iron stays as 3+. But some of the iron actually occupies the sites of a nickel 2+ as iron 2+. So that happens quite often. It depends on the synthesis process, but it's quite common to see that. And one of the things that happens when you have that iron 2+ is that so here, if we have iron, oxygen, nickel, if one of those nickels is substituted by an iron 2+, what we're going to have is iron, oxygen, iron. And it seems like, without going into a lot of detail, it seems that it's been published that this iron, oxygen, iron seems to be very beneficial to lower the activation energy to do this reaction. So I have to say that this catalyst is really good in alkaline environment, not in acidic, unfortunately. But this is a very promising material, and it's being researched by us, but it's being researched by a lot of people at the moment because it performs really well. So how do we prepare these materials? So we prepare the fibers as the way I mentioned before. So we have fibers that we use that we have prepared by electrospinning, and what we do is an electrode deposition, which is a very flexible, easy method of fabrication that enables to attach any layer of materials by putting precursors in the solutions. So we put iron and nickel, and what we end up is with these fibers. That's an SEM, but then if we have a look at the high resolution TM, we can see here the fiber, and we can see here the crystallites of nickel iron hydroxide, and here an even higher resolution we can see in more detail how we have the amorphous carbon here, and then we have the crystals there. So it's quite easy, let's say, to prepare, and obviously there's a lot of things involved in the process, but you don't need a lot of things to produce these materials. And what we do is change the conditions a little bit. So we did to see what happens when you change modify the parameters. So we did one on the nitrogen flow, and then we did another one on the static gas. So this is called nickel iron N2, and this nickel iron N. So to characterize these materials, we use a gas diffusion electrode. This was in collaboration with the University of Copenhagen. What we do here is that we put our catalyst here. This is very handy for us because usually when you will do to try to characterize the material for oxygen evolution or reduction is to use a rotating disc electrode. What happens with that is that you need to prepare an ink and then sort of like drops into your rotating disc electrode. We don't want to do that because we want to actually be able to test the freestanding mat as it is. So we were really lucky to find this group, and that they have this system where you put your freestanding mat here, and then the gas is going to flow underneath, and then we'll be in contact with the catalyst layer, and then we have like an amphion membrane, and then we'll have an electrolyte. So it's quite similar, quite close to the actual conditions in a water electrolyzer, for example. So this system allows us to study our electrodes for oxygen evolution and reduction. I have to say that I'm only going to present here the results that have to do with the oxygen evolution, because I think they're the most excuse me, the most interesting ones, but we also have oxygen reduction. So this material is actually a bifunctional oxygen electrocatalyst. So it can do oxygen reduction and it can do oxygen evolution. So this is that's what a cathode in a metal air battery would need to do. So yeah, so here we have results of the testing. And I just want you to focus on, this is the hydroxide that's been prepared under flowing nitrogen, and the hydroxide that's been produced under static air. And you can see it's a massive difference in overpotential and in performance. So this was quite intriguing, because we thought something might be different, but we didn't thought it was going to be so different. And then here, if we have zoom into this area, we can even see a little bit more the peaks that correspond to the nickel redox reactions. And in green, actually, we have our standard, which is just the nickel without iron, and then we have the nickel iron prepared under flowing nitrogen and the nickel iron prepared under static air. And then you can see how different those peaks are, and quite shift they are, especially interestingly versus just the nickel as well. So knowing that this corresponds to the nickel oxidation, so that's quite intriguing as well. We still don't have an answer for that. So we're still working on trying to understand what's going on. So we did different tests. So I'm going to show you XPS. Yes, I mentioned it's got some iron 2, so we find some iron 2 as well, so it's not surprising. And then we do some XRs and diamond synchrotron to try to understand what the difference was. So it doesn't seem to be something in the bulk, because both the one preparing nitrogen and the one preparing air seems to have like the same XR spectra. So that was also surprising. We were hoping to see some sort of differences in structure that way, but we couldn't. And then the latest thing that Link's been trying to understand is they try to combine the ICP measurements with XPS measurements. And then what she's found is that in the case of and this could be very key to understand this, is that in the case of material prepared and the flowing nitrogen, we have the surface contains a little bit more nickel than in the case of a one preparing static air, which contains a lot of iron. So that might be it. So and that might be why the bulk seems to be the same amount. So that might be why we are getting this difference. That might be the key, but we still need to know why exactly. So one of the things that we're trying to understand is whether there is anything to do with the with the way that these irons and nickels are coordinated in the structure at the surface, essentially. So yeah, but what we are finding is that summary, they perform really well. This here, the first column is our work, and then this is the rest. So our overpotential is not the best, but it's not bad, which is very good. Is our kinetics, our TAFO is the best. So we are really pleased with that. We just need to the last bits of understanding to really be able to understand the system. But yeah, so these are the two different uses of these sustainable materials that I wanted to introduce to you, all related to batteries. One is stationary, like redox flow battery, this one metal air batteries. So and I think with that, I'm just going to conclude and just want to thank my group, all my collaborators, the funding, and to you all for listening. And I'll be really happy to take any that you have.